My name is Abrek Emmanuel, and I'll take us to the first part of the presentation of the knowledge distilled large vision models for accessible guide-based screening of skeletal disorders. We shall go through the background and introduction. Now, skeletal disorders like osteoarthritis, scoliosis, and Parkinson's pose major health challenges, especially in regions with limited access to specialists, because these diseases need to be detected early, but most times these abnormalities will go unnoticed or ignored, leading to delayed diagnosis and worsening of the outcomes. Now we can have video-based gait analysis to capture subtle joint movement and patterns associated with these conditions. Now, this project that we are dealing with, it's to develop a knowledge distilled large vision model that combines vision features and clinical embeddings to detect these skeletal disorders. Now, that video model, its knowledge will be distilled into a smaller model that can be optimized for mobile development so that this model can be used on low-end devices to provide accurate, explainable, and scalable early screening like on low-end devices and low resource settings. Now we shall talk about related works and recent trends. Now, we shall look at this study by Maurizio and Codiero and his colleagues at the Department of Engineering and Informatics and Technology at the University of Shannon. Now, for them, their research was based on okay, it was based on predicting gait stability for older adults by integrating computer vision with synthetic data generation. They were facing a challenge of few data sets or little data, so they came up with an engineered solution to synthesize their own data. Now, this data had similar properties to real life data, as you can see in these graphs. The synthetic data shares so many properties with the real life data, and they're using features like margin of stability, step width, also indicators like body mass index, fall history, and identified through the sharp analysis. So the the models they trained with synthetic data and real data heavily outperformed the models that are trained just on real data. So they came up with a solution of creating synthetic data to meet the problem of low data sets or little data. Next, we'll talk about the domain application problem. As we have discussed, the skeletal disorders like scoliosis and Parkinson's, they present a major health problem here in Uganda and other resource limited regions, where orthopedic specialists are really few and far between. These gait abnormalities have early signs, often reflected in asymmetric stride length, reduced hip extension, abnormal strength, and to an untrained eye, these signs easily go unnoticed. So these patients normally have delayed diagnosis, which could actually worsen the situation. So this gap in accessibility to screening uh, highlights a need for local scalable solutions that can be used to detect these abnormalities early, even in rural areas with that are under resourced. Now, of course, we have talked about our computational problem. Of course, there is the big problem of data limitation. Now, this global data, we normally have global data sets, but the ones representative for African populations are really few, so we could have potential biases. Then, computational constraints. Now, these large vision models are really resource intensive, so it's really difficult to deploy them on low-end mobile devices. That compromisation and optimization. Then there's label scarcity. Collecting large data sets in Uganda is really challenging. First of all, specialists are few, and many of them are affected are in rural areas. Then explainability gap. Now, these deep learning models that we intend to use normally function as black boxes. So it's really hard to explain their methodology to medical personnel. Next, we have to talk about the objectives of the project, and of course, the objective one is to implement a teacher-student distillation framework for transferring knowledge from a high-capacity LVM or large vision model to a lightweight mobile model. Then also develop a mobile-ready guide screening system. This will be a mobile application, and it will be used for actually screening videos and giving out recommendations. Then to integrate skeletal key points and clinical knowledge embeddings for accurate detection of skeletal disorders. We want to provide interpretable diagnostic outputs with risk scores. Now, these will be on the interface of the application, and they will be there to support the health workers, the specialists and non-specialists. So now we move on to the research contributions and outputs so far. So we have built a multimodal dataset for video images and clinical embeddings for different gait-related conditions like Parkinson's, myopathy, and cerebral palsy. We also use MediaPipe to extract 33 skeletal key points from gait videos and harmonize them into a clean dataset and carried out EDA on it, pre-processed it, and did the removal of null values and duplicates. Then we've also fine-tuned an open source gait model on the video dataset to detect skeletal disorders. We fine-tuned it with our own videos. Uh, then I've also developed a teacher-student knowledge distillation framework whereby the student learns from knowledge from the large vision model, so that it's much more, such as a smaller model that can be deployed on mobile. So this will serve as a summary of what I've discussed so far. We shall have data collection from an open source dataset like GovD. Then we shall pre-process these standard videos using a pose estimation tool like MediaPipe. Then of course shall move on to clinical knowledge integration, extracting guide biomarkers from the orthopedic literature. Then of course the model development, we shall use that knowledge teacher-student knowledge distillation framework, whereby the model is fine-tuned with skeletal disorder and clinical embeddings. Then that knowledge is distilled to the student for a much lighter weight model that can be deployed on a mobile application. Then, of course, the training and evaluation, we shall use semi-supervised learning, and the metrics that we shall use are accuracy, precision, efficiency, and explainability. Then, of course, at the end, we shall shall have the deployment phase, whereby it will be deployed on an offline fast architecture. Then later on, it will have the streaming.
All right, Joseph here, and I'm taking you through dataset description and the explanatory dataset data analysis. To begin with, the dataset itself was extracted from GAVD, which is a gait abnormality in video datasets. And in this dataset specifically, it provides features uh, which are specifically the URL links to different videos, the gate sequences and frames, which all reflect a given gate. Some are for normal, abnormal, and even mentioned specific musculoskeletal diseases. So in these videos, uh, we shall first specialize, lower our scope to the three most specific diseases, as one of the discussants said earlier on, that is Parkinson's disease, cerebral palsy, and mathopathy, or sometimes called mathopathic gait. This had all videos with which links were obtained and videos downloaded. With the help of MediaPipe, were able and PyTube, these videos were downloaded and frames extracted. With the help of MediaPipe and OpenCV, for EDA, exploratory data analysis, we had to extract the 33 landmarks using pipeline, of which this was then visualized as a time series for these three different kind of musculoskeletal disorders, and analysis was later done on. So what I derive mean in this slide is that the data set itself prior was video based. However, to extract more data that was later converted into a CSV for analysis, we had to use MediaPipe and OpenCV to help us to achieve that. For visualization, many graphs were drawn, and they illustrated how the different key landmarks varied across the three different gait patterns. That is, as said earlier on, the Parkinson's disease, the cerebral palsy, and pathetic. So, according on the amount of data that was extracted per each disease, that was is what we see on the left here. We had pathetic having the highest amount of data, and it decreased in that ratio. So all the 33 landmarks were extracted, but to analyze this, we had to get key features within the extracted frameworks that we would use for basing on how we can assess the difference between these three different gates. So the left hip, the right hip were compared, and these were the graphs that were generated. And then other shoulder parts that involved, because MediaPy provides coordinates in 3Ds. So with the flexibility of media pipe, we can visualize all the different records received, and then even the visibility that was registered during capture. More visuals included the correlation matrix heat map that studied the correlation. I mean, the how data between the key landmarks varied as recording was carried on. And then also we try to look at uh, at how these uh, data can be differentiated. But however, when we visualized with the PCA analysis thing, it just formed some aggregation which was complex to distinguish. However, other methodologies can be applied to this for more. Uh, more included visualizing different body parts, just like it was said earlier on, but using other different features to just get appreciate the difference between these three different types of disease, and different graphs like this were generated. And then also each feature along a recording session was graphically showed, and then even the corresponding visibility for each illustrated as seen in the slide. And then finally on how to analyze each disease for all these features, different graphs were also generated, and this were looked, and these were those that represented all the different time series collected in all the recording sessions in the data frames.
So the student model is quantized, pruned, and compressed, making it suitable for mobile devices with limited processing power. So we couldn't use the parent model because it is a large visual model. So we decided to use the student model for deployment because it is smaller and its capacity is suitable for the mobile devices. Then two, we have memory footprint, significantly smaller than the teacher model or the parent model, fitting within typical smartphone RAM constraints, similar to the previous one. Then its inference speed, which is optimized for real-time gait analysis on low-cost Android devices. And then we have its offline capability, of which it can run without internet. And we know that we are building an application that is going to be easy for the people in our country, in Uganda, and most people find it hard to access internet. So the student model has an advantage of having offline capabilities. And then our scientific justification for using the student model is that one, it has knowledge preservation. So despite its compression, it retains essential diagnostic knowledge from the teacher large visual model through distillation. So despite it compressing the data or what it's using, it is able to retain essential diagnostic knowledge. And then we have clinical accuracy, whereby it maintains sufficient diagnostic accuracy for screening purposes while being deployable. And then its explainability, where it uses integrated graph-based reasoning module, and it provides interpretable clinical outputs. So its outputs are interpretable, they are easier, and it uses graph-based reasoning. And then we have generalizability, where it is trained on both global datasets and locally obtained datasets or locally obtained gait patterns. So our deployment pipeline and system architecture is as follows. One, we're going to have 3 stages: the input stage, the processing, and then the output. So for our input stage, we're going to use a mobile phone camera to capture the gait patterns or a video in real time. Then we'll have pose estimation, pre-processing, and that is through media pipe. And then we'll use skeletal key point extraction. Then so the mobile application is going to be connected to your phone camera. So when you open it, you're able to take a video, to record a video, or input images of a pattern recognition. And then during its processing stage, the student model inference, we're going to have feature extraction from the gait sequences or the video that you've uploaded. And then we're going to have knowledge graph reasoning module. And then our output stage is that it's going to give you a risk score calculation, and it's going to give you clinical explanation generation and visualization overlays on the gait video. So all you need to do, you open the app, and then you input, you record a video of a pattern, maybe your hand, it could be the hand, it could be the whole body, and then during its processing, it extracts the gait sequences, and then its output is going to be a risk calculation, and it's going to give you clinical explanation and visualization overlays. So our main interfaces, due to space, I was unable to include the interface screenshots, but then in the next slide. So we're going to have a home screen with an option for recording a video or a live analysis, and then you'll have previous screening history so that you're able to track your history, and then you're going to have the camera screen, the analysis screen, and then the screen that shows you recommendations of the predictable disease, and then the recommendations. So those are our interface examples, where we have the home screen and then the analysis results, where it shows you the gait abnormalities, and then it will show you the recommendations. So those are the steps: open and start, position, record a video, and then the app shows a real-time skeleton overlay as you walk naturally for about 10 to 15 steps. And then the AI analysis, where your phone's AI processes the walking video locally and privately, and that's no internet required. Then the system will analyze your stride length, symmetry, joint angles, and in about 2 minutes show you progress as it works. And then after, it will give you recommendations according to the abnormalities detected. Then our IP assets, we have software IP, that's intellectual property, where we have copyrightable assets. So our Gait Check mobile application is going to be complete software code based, and then our user interface design is going to be a unique UI optimized for healthcare workers, or sorry, I missed out something here, healthcare workers or any other person, because we want it to be accessible to the community, so any other individual in the community, not necessarily healthcare workers. And then clinical decision support algorithms, that will give you scores of your gait movement patterns and according to the analysis. And then we have data processing pipelines where we have pose estimation and feature extraction workflows. Then our trademark assets, which is brand protection. We're going to call our mobile application gait check, which is the primary trademark for our mobile phone application. And then we'll have a logo and visual identity, which will be a distinctive branding. And then we have a tagline, which is gait analysis for health screening. And then our data sets, we're going to have Ugandan gait database, which are locally collected. And we'll have annotated clinical correlations where gait patterns are linked to informed diagnosis. So our conclusions and limitations. So first of all, our significant outcomes. Successful knowledge distillation. Well, demonstrated that complex gait analysis can be compressed down into a mobile phone application that is deployable while retaining that diagnostic accuracy. And then we're going to be having a real-world accessibility, where we proved that advanced AI gait screening can work offline on smartphones. We'll have clinical integration, where we'll have successfully bridged the gap between AI predictions and clinical reasoning through explainable outputs and knowledge graph integration. And we'll have consumer adoption potential, where the interface design shows the technology can serve both healthcare professionals and individual consumers, like I said in our previous slide. So Gait Check, which is a mobile application, will successfully demonstrate that large-scale gait analysis knowledge can be distilled into accessible mobile technology, enabling early skeletal disorder screening and detection in both clinical and consumer settings, while maintaining privacy and offline functionalities. So the limitations that we are having so far, one, we're having limited validated clinical data, where we're lacking large-scale clinical data sets linking gait patterns to confirm diagnosis. And the solution is that we'll partner with Uganda medical institutions for prospective data collection. And then one problem that we'll have is that user positioning and technique matters, because proper phone positioning and patient cooperation is really needed, and it will affect the results. So a solution is that we're going to add real-time guidance features, automatic quality checks, and also an option of retaking prompts for having suboptimal recordings. And then computational constraints, while having the large vision model, which is resource intensive, and making deployment on mobile devices quite hard. So the solution that we're having is knowledge distillation, as we said, where we'll use a parent model as the large vision model, and then a student model, lightweight for deployment on mobile phones. Our next steps, one is going to be enhanced model training, where we'll have knowledge distillation pipeline development. Then two, we'll have mobile app development. We'll have core application architecture, such as cross-platform frameworks. Then recommendations for further research. We'll have one, we're suggesting multimodal integration, which is combining gait analysis with voice patterns, cognitive assessment, and wearable sensor data. And then longitudinal studies, where we'll track gait changes over time in order to improve early detection capabilities. And then intervention effectiveness, where we'll measure how gait screening impacts patient outcomes and healthcare costs. And then we'll have suggesting community training, such that we can optimize training programs for effective technology adoption. Lastly, our acknowledgements. One goes to our academic and institutional support, where we extend sincere gratitude to our supervisor, Dr. Galiwango Marvin, and our course teammates at courses for providing a framework and guidance that enabled this research project. Then we acknowledge the creators and maintainers of the open source gait datasets that have formed our research basis. And then we extend special thanks to the healthcare professionals and researchers whose published work in orthopedic literature provided the clinical knowledge embeddings that inform our AI models, diagnostic reasoning, and we look forward to potential partnerships with Uganda health institutions for future clinical validation and deployment phases. Thank you so much for listening.